In question 1, we're trying to verify that our inverting integrator is working. And one way to do that, in a simple way, is to put in a pulse. And so if you have a pulse, what you have are, for moments of time, a constant voltage, which if you have a positive constant during that time when you integrate, you should get a negative slope. And if you have a negative voltage, you should get a positive slope. And so you can rapidly see whether your inverting integrator is doing what it's supposed to be doing. And we can see in this LT spice that, yeah, we're getting a negative slope for positive voltages, positive slope for negative voltages. But notice that the peaks are rising in time. And in fact, I can calculate the slope of that to about 12 milliseconds, 12 millivolts per second, just by eyeballing this graph. Okay. Well, that means we are integrating some kind of positive signal, and if we look, we see V offset in this case is 10 millivolts, which, if we look at this equation, V out equals V offset times 1 plus 1 over RC dt, which V offset being a constant, can be considered a constant, will give a positive slope. So, what are the solutions to this? Well, you can choose an op-amp with a small V offset, like the LT1001, or you can use the V offset tuning pin on an op-amp, which you can read a data sheet to tell you how to do that. Or you can use a large feedback resistor, such like that. Unfortunately, that feedback resistor, in order to counterbalance the 10 millivolt offset, tends to be small, and it starts to act like a filter, and you don't really get the DC performance that that you would like. Question 2, let's estimate how many parts we're going to need for these differential equations. Now, if you have two differential variables, in this case we have x and y, that means there's going to be at least 2 op-amps, 2 resistors, 2 capacitors for the 2 integrators. All right. Now we also have 2 initial conditions, which means we have to add in 2 other op-amps, and depending on how they're configured, 3, maybe 4 resistors times 2. The x squared comes from a multiplier. Now if I just do a rough diagram and not really setting the resistances, you can see 1, 2, 3, 4 op-amps, 1, 2, 3, 4, 5, 6, 7, 8 resistors. I'm just taking the initial conditions in this simple way, and I just have the multiplier. And if that multiplier was divided by 10, you can easily alter this resistance to handle it. You don't need another gain stage. Now we need to design this differential equation. All right. We've gone over this quite a bit, so I will present 2 solutions. One, we have the inverting integrator, and I've just taken B and inverted it, so that when we have minus Z and we invert minus B to plus B, we'll get minus B over here, and then we have a gain of 1. Now, I like this solution because I don't have to invert B. Inverting usually involves another op-amp somewhere for an inverting amplifier. So if I use this configuration and keep tight tolerances on my capacitances, I can bring in B here. And then on the initial condition, if I use this configuration that we've talked about prior, I can get my 2 volts of initial condition there. We have another integrator issue. We're trying to verify that this integrator is working. And this time, I've just tried to use a constant input. And a constant input into an inverting integrator should give me a slope. And in fact, it does. But I've also have a variable that's checking whether my circuit is working properly. And I notice, yes, I get slopes, but the check has a much higher slope than the slope that I'm observing. And when you start to see that a circuit can't keep up with a slope, and also when I calculate the slope of V out, I get something that is close to the slew rate. And when I look at the slope of the signal, if it were ideal, it's greater than the slew rate. And we can see that the slew rate is 100 kilovolts per second. All right. Now, how do we solve this problem? Well, we can get a faster op-amp, or we can scale the equation either in voltage, time, or both, so that we're not slew rate limited. And if we're doing an analog computer, that kind of thing is easily done. Here I want you to design an experiment that shows the effective gain bandwidth on an op-amp based circuit. What do you need? You need a function generator, scope, probes, power supply, boards, wires, op-amps, data sheet, and resistors. Now the trick is that if I took the open loop gain at 0 hertz, or very near 0 hertz, and the gain bandwidth, I'd get this triangle of possible things that I can design. If I choose a high gain, let's say 100 or 40 dB, I would get a Bode plot that would trace this out. Okay. Now, why choose 100? That's because the frequencies that I'll have to measure in order to see this effect will be small enough to be done on a proto board in lab. If I choose a buffer, I'd have to go out this far in frequency to notice the effect. And if I choose my input vectors wrong, I could actually show slew rate limiting. So choose a gain of 100. You could use something else, or 40 dB. And I choose an op-amp with a high open loop gain level of about 100. And that means the DC open loop gain is a lot greater than the gain that I want to use, and that means there's no finite open loop gain effects that will affect my circuit. So if I choose R1, R2 as 1 mega ohm, R1 is 10, and a part with a high Rn, which would be greater than 1 mega ohm, I won't have any finite Rn effects of the op-amp affecting it. Also, to prevent slew rate, I keep the amplitude of the input vector times the gain times 2 times pi, right, which is the maximum slew rate, a lot less than the slew rate. That way I can't possibly be slew rate limited. Then I'll calculate the frequency of interest and take some 5 data points above and 5 data points below. And in that way, I should be able to demonstrate the effect of gain bandwidth and not see effects of finite open loop gain, slew rate, and if I put a capacitor on the output, I shouldn't see any drift due to V offset as well. Here we need to extract the saturation current and the ideality factor of a diode. And if you look at the numbers I use for the slope, I get a slope of 20, which leads to an ideality factor of about 1.93, which then I just find the B-intercept, right, which could be done graphically as well. Okay. So I get about minus 16. And so when I put this into the equation, I get about 1.12 to the minus 7 amps.